Well, hello everybody. As long as people is starting to come from the last poster sessions, I would like to welcome you all to the conference from Professor Thierry Boschk, from whom I will make a very brief introduction. It's really a pleasure for me to introduce Thierry here. Thierry is one expert in the world of distance measurement sensing using lasers and using different type of electronic arrangements. He is especially an expert in the field of self-mixing interferometry, which is the topic of his talk today. So we expect to have a very nice introduction to the field of self-mixing interferometry. Just as a list of positions, Thierry is currently a research scientist at Toulouse, where he has been the boss of the his lab in the last CNRS facility. He's currently full professor at the Institut National Polytechnique de Toulouse, and currently where he is their vice president in charge of corporate relations. He's strongly committed to technology transfer, and he has led the creation of a joint-led laboratory with ACOM, a company, since 2017, and is currently the vice president of the French chapter of IEEE Instrumentation and Measurements since 2019. He is going to introduce us in one of his fields of specialty on unusual ways of using optical feedback interferometry for sensing. And as long as I've been asked to be brief by all parts, I don't want to extend that anymore. So Thierry, thanks very much for accepting the invitation, and the floor is yours.
So thanks, Santi, for this kind introduction and also for this invitation, of course. Okay, I will first remind a little bit of optical feedback interferometry, also called self-mixing, and after that I will discuss some unusual ways of using it, okay? So just as a reminder, usual interferometry is a complex system with a lot of external optical components, and we try to do something, well, similar, not equivalent, not as accurate, of course, by removing almost all those optical components, but the lens, the focused lens. So the idea is to use, in fact, a laser and the photodiode inside the same package, which is the case for DFB and Fabry-Perot laser, for example, and then obtain something similar to what we should obtain with a complex usual interferometer. Of course, sometimes we have no photodiode on the back face of the laser. That's the case of the XL. In this case, we can monitor the information just playing with the junction voltage of the laser itself. But basically, the best solution, the best signal-to-noise ratio will be obtained if we have in the same package a photodiode at the rear face of the laser itself, like in this case. So what are we supposed to do with this? So basically, the system is based on the fact that we are emitting a laser beam in direction of a target. The laser beam is backscattered by the target in direction of the active cavity of the laser here. And then this laser beam, backscattered by the target, is mixed with the standing mode inside the laser. So it means that the laser beam, which is reflected by the target, will interfere with the laser beam which is not yet emitted. And then we will get what we call optical feedback interferometry, or self-mixing, as the laser beam is mixed with itself somewhere in the active cavity of the laser. So what happens in this case? In this case, the laser power will be modulated this way, for example, and we try to get information from this modulation of the optical power, which is monitored by the photodiode at the rear face of the laser. So it means what? Sorry. It means that the laser diode is the optical source. This is not a scoop, of course, but it also plays the role of the microinterferometer as interferences are occurring inside the active cavity of the laser itself, and we will monitor everything of the signal, the useful signal, with the photodiode in the same package inside the same package here, so at the rear face of the laser. It means that we only have a lens as an external optical component and nothing else in comparison with usual interferometry. So of course, it's low cost, it's very cheap, it's only a commercial laser. like those we can find, DVD reader and so on. It's integrated because everything will happen inside the active cavity, which a length of 100 microns, for example. It's purely self-aligned, and we can use it with a maximum range up to, let's say, 10 meters, even if most of the time it's limited to 2-3 meters. But it can happen that we can use it up to 10 meters, for example. We will see one example later. So, of course, if the hardware has been simplified, we have removed all those optical components, there is a price to pay, and this price is the fact that typically the shape of a signal is much more complex than what we should have with a sinus interference. So we could have here sort of like signal, we should have hysteresis, the amplitude of the fringes can here decrease, the number of fringes is not constant, and so on. And everything depends on what we call the coupling factor C here, which is function with the reflectivity of the target, the distance to the target, and so on. So, in fact, the complexity of the system will be shifted from the hardware to the software because we have to do a lot of physical model and also a lot of signal processing to adapt those signal processing to every shape possible of signal we have to monitor. So the first application I want to speak about is vibrometry. As Santi has said, we have created a joint laboratory with a French company called ACOM, and most of the activity on vibrometry is now in common with this company. So the joint laboratory is funded by the National Research Agency in France. And first, I will give you a basic idea of what we are doing traditionally. So first, as usual, we have a laser diode, the photodiode in the interface. We are emitting the laser beam in direction of the target, which is moving, get back the information, and then we have this optical power variation. As we can see here, we have fringes. Between two fringes, we have a displacement of a half wavelength. That's very similar to usual interferometry. We have excess fringe here, but as we can see here, the shape of a sort of like signal is different if the target is going in direction to the laser, who's going away from the laser. So we have not only by counting the number of fringes, for example, the amplitude of displacement, but just looking at the shape of a fringe, we can also get the direction of the displacement. So that's really interesting. Of course, signal processing is not really simple. This is a two-step signal processing. For example, here we have what we call the phase enwrapping approach or method. Just for detecting the fringes, so counting the displacement by a step of half wavelength. So we have to consider here the optical power, then consider the inverse of the cosinus of the power, the derivative, and then we just get here, we're just detecting the fringes. And after that, we have a second block that may just optimize the displacement reconstruction by considering parameters to calculate this excess fringe. I will not enter in detail because there is a lot of signal processing, and this is not the goal of my talk today. After doing this signal processing, we have the possibility of reconstructing the displacement of a target. So this is the usual way of using self-mixing or optical interferometry, feedback interferometry, for displacement measurement. Now, something which is a little bit less usual is to use an autofocus with adaptive optics. Here we have used typically a liquid lens. We can see the liquid lens here and here, for example. So this is the complete system. With a laser, it's electronics, and let's say that 1/3 of the package is dedicated here to a battery for if we want to use it like a handheld system, for example. So it's absolutely not optimized. You can see the size of the system. And this autofocus using a liquid lens is not just here to focus the laser beam, it's also here to get the best shape of a signal to extract the maximum possible information about the displacement. So, in fact, we are not just using this liquid lens to focus, but to get the best signal for the optimized signal processing. So I think that, yes, normally it will work, I hope. Yes, we've got a movie here showing how it works. So it's not Spielberg, I'm sorry about this, but here we can see the lens and the laser with its electronics here. And we are using, typically here, a piezoelectric transducer actuator. Inside this piezoelectric transducer, we have a capacitive sensor, which is measuring the displacement of the PZT transducer. And we will compare, of course, the displacement obtained from the capacitive here sensor and what we are obtaining with the laser sensor. We will see this later. So we're just emitting the laser beam in direction here of the target and get information. And of course, we have a liquid lens here. So let's see it. We are 30 centimeters roughly, and we will see what will happen on the oscilloscope. So here, I will stop. This is the reference displacement of the target we get from the capacitive sensor. Here we will see the optical power variations, which is monitored by the photodiode at the rear face of the laser. And here we will obtain the displacement after reconstruction. So, okay, we can see here, for example, we have a first example of optical power variations and then reconstruction, but this signal is not the best possible. So we are still changing the voltage of the liquid lens to get a better signal, but this one should be okay. But we can see there is another one, yes. And here we have the optical power variations, and we have the displacement, which has been reconstructed by the laser sensor to be compared with the reference signal obtained with a capacitive sensor. And it's finished. So, sorry. Another idea was, okay, we have designed a micro interferometer, an integrated interferometer, so it's good in a small package. Well, not so small like a matchbox, but it doesn't matter. But if we still need for using it an optical table, because we are subject to vibration, it's completely stupid because we have something integrated, but we need something bulky to use it. So that's not good. So the idea was to design an embedded sensor, so to glue an accelerometer very close to the laser diode, and then to extract the whole information. Of course, if typically we will see some example, if I'm using this complete sensor without an optical table, I will get the displacement of the target plus the displacement of the laser head itself. And the accelerometer will help us to extract the information. We will get from the accelerometer the information about the displacement of the laser head, and then by data fusion, extract from the global displacement, the displacement of the laser head, and then get finally only the displacement of the target. So it was an idea we patented some years ago, and then we win the European Mechatronics Awards 11 years ago. We are very proud of this, of course. I'm just kidding. And this is the experimental validation about how to use accelerometer with our laser sensor. So typically here, we put different accelerometers just to compare them. We put this on a very bad shaker, so we get vibration in all possible directions, as we will see later. And we emit the laser beam in direction with the same PZT actuator with this integrated capacitive sensor, which presents a resolution of 2 nanometers, so that's quite accurate. Then, for example, here we are using the shaker with an amplitude of 1.5 microns at a frequency of 225 Hertz, and the PZT was moving with an amplitude of 2.5 microns at a frequency of 45 Hertz, for example, 47, sorry. This is the global displacement we have. This is the displacement which are measured by the accelerometer with different axes along the axis Y, X, Z, and so on. And then we extract this displacement from the global one by data fusion, just subtracting in reality. And we can see here in red the reference displacement obtained by the capacitive sensor which is inside the PZT, and in blue, the displacement we have obtained with our laser sensor, and that's very, very similar. I want to specify that we use an accelerometer with a cost of only €4. So that's very cheap solution, and we are really focusing on low-cost solution for this kind of system. So here we can see another example. The target vibrates at 82 Hz with 5 microns amplitude, with a parasitic vibration at the same amplitude of 225 Hz. And this is the optical power, this is the global signal, and this is the reference motion or reference movement displacement we have, and this is what we have obtained after correction. It doesn't work only for sinus, it works even if the displacement is quite random. So here we have the same with reference sensor, so the capacitive sensor, and the reconstruction in red using our laser system. One key point, which is quite interesting. For example, we put our laser sensor on the shaker, and we are emitting the laser beam on a target which was not moving, and see what happens. And in this case, we can see this is the global vibration we get, which is purely parasitic. And here we have the signal corresponding to the displacement of a target, which is almost nothing. If I'm zooming, we can see it's not exactly perfect, but we are eliminating 96% of a parasitic vibration on this prototype. It means that only 4% are remaining when we are, in fact, obtaining those reconstruction. So it was using a liquid lens and using an accelerometer. It's not so usual. I think we are alone doing that. Oh, I forget, and I apologize, Santi, because effectively, when we are playing with liquid lens, we were working in collaboration with CD6 and Santi Roy at UPC. I apologize not mentioning this. I'm so sorry. You will appear next time too. I hope I will not forget this time. After that, we developed also optical feedback interferometry for velocimetry from solid to fluid targets. So traditionally, using a cell mixing sensor or optical feedback interferometer is like laser Doppler velocimeter. That's, you can see here this relationship, which is absolutely classic. We can measure translation, we can measure rotation, we can measure effectively the motion of the target along the laser beam. So that's very traditional, using a hard target. So I will just stand out two different applications we have developed in the past. Here we have developed a two-head system based on optical feedback interferometers. So here we have the lenses and the laser and its electronics. It's on a car, and we are pointing on the road, and this is the optical power we have obtained, plenty of speckle, of course. But finally, we get the velocity, even in case of a wet road, with a layer of water of 2 millimeters at quite small speed at this time. But we get here the Doppler peak corresponding to the speed of a car. So that's a possible application. So it was in the past. Now this is the newest system we have designed for scrolling measurements. So here we use it on wood, on paper, on metal, on glass, and so on. So it works. Well, it works quite well. And we have now a collaboration with a Switzerland company to develop and maybe commercialize this sensor for scrolling measurement on solid targets. So I will not give you more detail right now. Something which is less usual is to measure velocity of fluids. So this is an example of a system. So we are pumping some diluted milk. Why milk? Because it's a phantom, it's a ghost of blood. So that's when it's properly diluted, the behavior of milk is very close to the behavior of blood. And then we put it on a flow channel. We are measuring what happens in this flow channel with a laser and see what happens. So this is an example of what we have designed. So we can see, well, maybe it's not easy to see, but the channel, it's a big one here because the diameter of this channel is of 500 microns. Sometimes we are using much smaller ones. We have a laser sensor, which is here. We have a camera, a CCD camera, just to see where is the spot inside the channel, because the alignment is not so easy. Some electronics, data acquisition, and the pump to push the liquid inside the channel. Sorry. So what may happen? Depends of the density of particles inside the fluid. If the density of particles is very, very small, we will have what we call single scattering region. In this case, the contribution will be due to only one particle inside the area of measurement due to the laser spot. So that's very equivalent to a solid target, and we will have, as we can see here, for example, it's small, but it exists. We have a Doppler peak. So that's very, very close to what we have obtained, for example, with glass, with wood, or even with wood. If the density of particles is much higher, in this case, when we are emitting the laser beam inside the channel, we should have some multiple scattering. So we will have, for example, laser beam will be reflected by one particle, but maybe this reflection will also be in another direction, and then we will have a reflection with another particle, another one, and then get back. So in this case, we have, of course, no Doppler peak. We have Doppler shift randomization, of course, and in this case, we will have this kind of signal, which is much more complex to proceed, because, of course, the information is not as clear as in this one. So if I'm speaking about single particle detection, we can see here two examples of Doppler peak with a particle with a size of, let's say, 200 nanometers, and another one with 550 nanometers. So we have Doppler peaks here. So that's quite usual. So without particle, this is the flow we have detected, and this is the Doppler peak that has been detected here with one particle in the area, in fact, of a spot size, the laser spot, sorry. If I'm not considering the Doppler frequency, if I'm considering the signal in function with time, we can see we have a sort of burst. This one is small, this one is much easy to see. So the burst is different in both cases. So it paves the way maybe one day to be able to do some sizing. So not only detecting the velocity of a particle, but also maybe make a sort of classification of a particle in function with its diameter, for example. Well, we are not ready to do that. It's not robust enough right now, but we can see that the burst is different. So maybe one day we will be able to do that. Fingers crossed. So here, for example, we use as a particle polystyrene with a concentration which is very, very small to be sure that we have only one particle in the area which is created by the laser spot. I'm just checking the time. Okay. Multiple scattering is much complex, but unfortunately, it's probably much more common also in real life. So here with our laser system and a lens, we will focus inside the channel and try to get some information. For example, here in the time domain, this is the blue signal. It's not easy to see something. We are doing FFT. And in blue, we have the signal obtained with the fluid which is flowing inside the channel. And when there is no flow, this is the green one. And in fact, we will make the difference of the moment of the optical feedback interferometric signal with flow and without flow. In fact, we should say this more simply by saying we are just considering the difference between both signals and calculating the area equivalent of the difference between the blue curve and the green curve. So difference of both signals. So here we have a system with the electronics, with a lens, with a laser, and a translator stage, typically. And we will do it on my arm. In reality, this one was my arm, effectively. Yes, the left one. And we put some irritating cream in this specific area. And then, using the ZEBA stage, in fact, we translate the laser beam from an area without the cream and an area where the cream was put on my arm. As we can see here, after 1 minute, nothing happens clearly. Well, it was quite equivalent. But after 10 minutes, well, it was 11 in green, we can see here that this is the area of my skin where the irritating cream has been applied, and we can see effectively some vascularization. So we can see that we can detect something. In fact, the blood was flowing more with more speed, more fastly. And after half an hour, we can see that it's coming back to normality. So the efficiency of the cream was about something like 40 minutes or something like that. It's not yet exactly the same, but it's coming back to the blue one. So with such a system, we are able to detect blood flow and then vascularization. So we have participated to a European project with SANTI, with UPC, and also with the University of Queensland in another project. And we try to design a system for detecting skin cancer. And this is one example of what we have obtained with a nevus and a melanoma. We can see that the bandwidth of a melanoma is much higher than a nevus. So maybe we should classify effectively some skin cancer in function of their, if they are malignous or not so much, clearly. It's pitiful that this project has been stopped because there is no more money, but I hope that in the future we will continue working on this. The results were not exceptionally good. We have not obtained something really exceptional with this system because it was not robust enough to be used in an hospital. That's pitiful. But it was just a problem of mechanical engineering. And I think we have solved this. And now, if we should do some more experiments, it should be interesting to see if we are really good in detecting nevus versus melanoma, for example, and which percentage of success. Here we have another example of what we have developed with a French company we have contributed to create. It's a startup company in Toulouse called Epsilon, and they are commercializing an anemometer called now Wind Eagle. That's a big name. It's a short-range lidar measuring directly in front of the blades for wind turbines monitoring and optimization. It's for windmill implementation, but also it's for optimizing the angle of the blades in function with the direction of the wind. So here, some performances we have obtained. We are detecting a particle size of only 1 micron at a distance of 10 meters with a cell mixing signal. It was 7 meters in the past, and we hope to do it at 15 meters, so out of the vortex of the blades. So in fact, we will detect really the direction and the velocity of the wind, and not the direction and the velocity of vertex due to the blades. We're able to detect more than 1 particle per second using 2 different laser beams with a wind angle detection of plus minus 60 degrees and a velocity up to 25 meters per second, which correspond to what the user are asking for. We're using a wavelength of 1.3 micron, and this system is working from minus 25 degrees to 50 degrees. So, of course, it works in Finland, in Canada, and I don't remember some other foreign countries, of course in France, but some other foreign countries. We commercialized this system 2 years ago. The optical head is quite, well, the weight is quite important. It's almost 20 kilograms. Of course, we don't want the sensor to move when there is too much wind, so that's normal. This is not the weight of a laser, of course. This is only the weight of mechanics to be really stable. Something new we are developing since some years now, it's acoustic measurements using cell mixing. I'm checking the time. Okay, I will be in time. For example, we are doing some sound field visualization using this cell mixing or optical feedback interferometry system. In fact, when we are emitting a laser beam here in direction of a target which is not moving, if at the same time we are also emitting a sound, so an acoustic wave, this acoustic wave will disturb the optical path difference, because in reality, if I'm considering the change in optical power variations given by this relationship, we will have here a variation of refractive index due to the propagation of the acoustic wave. So it means that it will be equivalent to a displacement, even if the target is not moving, but what we will measure will be equivalent to a very small displacement. So this is the system we have designed first to make the proof of concept. So we have a laser pointing on a target which is not moving, and we are emitting an acoustic wave, and then disturbing the propagation of a laser beam, disturbing, in fact, here the refractive index, and see if we are able to measure something. So the very first experiments we're using an ultrasonic piezoelectric transmitter at 40 kHz. We can see here the peak. And just by moving here, we have a rotation stage. By moving the sensor point to point, we were able to make a sort of topography of propagation of the sound wave. Here we have the traditional propagation. And here we put an obstacle in the room, and we have a propagation and the reflection of the acoustic wave. So of course, it's long. We need to move the laser head step by step, so it doesn't work with a sound which is transient, and it may be very stable, of course, because we need several minutes to do this cartography. Then here we have a laser pointing the target, and here I have a loudspeaker emitting a sound and a microphone just to compare what we are measuring. And I will try to make you hear what we have recorded using this laser microphone. So it's really noisy in comparison with a traditional microphone, of course, but we are not trying to be in competition with those microphones. We want to detect in reality much more acoustic waves, and here, effectively, our system is really interesting, as I will show you. So, as I said, I'm checking the time. Oh, right, okay. The equivalent displacement will be very, very small. So it's not even an alpha wavelength, so we are not counting the fringe in this case, unfortunately. But fortunately, if the equivalent motion is smaller than the alpha wavelength, it will be linear. It means that if we have a displacement, an equivalent displacement, which is sinus like this, the optical power will have the same shape. So it will be directly linear when we have no fringe. That's really interesting. We use the SEDOPTICA model, for example, to make an equivalence between the displacement and the variation of a refractive index. And this is an example of the experiment we have done. We emit here an acoustic wave in this tube. We have a microphone just to check what we have obtained. We have just behind here the laser. Here we have the target which is not moving. And so the laser beam passes through this hole, and then we are measuring things. What we have obtained is we have detected with this experiment a maximum power of, let's say, 100 dB sound pressure level. So it's equivalent to a displacement of 500 picometers. And the smallest displacement we have detected, very noisy, very inaccurately. The accuracy was about only 20%, so that's very, very poor. But we detect something equivalent to a displacement of 200 femtometers. So due to the variation of refractive index. Here, we also use our system to make the characterization of metamaterials. For example, here, an acoustic cloak. So it means that this cloak with a periodical structure with a dimension which is smaller than the acoustic wavelength, we want to see what happens inside and what happens all around. It means that if we put an object inside this acoustic cloak, in fact, the propagation of a wave must not be disturbed at all. And we will verify if it's true or not. So we use a speaker here, we use the clock, and then we emit the laser beam in direction of a reflector and measure the propagation of the acoustic wave. So this is the experiment. So here, this is the acoustic clock. We put an object, just a cylinder, in the middle of the clock. It doesn't matter if there is an object or not. Here we have a speaker. We move the speaker to make the cartography because we are measuring those refractive index variation all along the laser beam. So it's a step-by-step system. It's very long. Here, so we have the laser system with a photodiode, the lens. Here we have the reflector, which is not moving. And then effectively, we can move all the system to make the cartography. And this is what we have obtained. And we can see that if we are emitting an acoustic wave, it will pass through this acoustic cloak and the propagation is not disturbed at all. So the neutral effect of a cloaking has been demonstrated by this experiment. Here we are also characterizing another metamaterial, which is an acoustic focus lens. It's different layers of balls with a diameter of, let's say, 40 millimeters, separated by 15 millimeters from each other, with an acoustic frequency of 10 kilohertz, so an acoustic wavelength of 3 centimeters. And the idea was to check if effectively this metamaterial was playing its role of focusing lens, if a focus point was moving in function of a distance between this metamaterial and the speaker. So here we have typically some results. If we put the speaker at 6 centimeters from the acoustic focus lens, we can see here the focus point. If the speaker is at only, let's say, 5 centimeters, the focus point is moving, at 3 centimeters, moving away, and so on. So effectively, we've been able to characterize this, the behavior of this metamaterial. Something else I will try to do, fastly. We have developed and patented some tomography. So the principle is first we are obtaining a one-dimensional image through different angles. So we are rotating around the target, for example, and we get what we call sinogram. And then we are constricting by inverse of a random transfer. We are creating an image from the projection data associated with this cross-sectional scan of object. And then we are doing this step 1 and 2 different altitude. And then we get the three-dimensional image. Here again, that's very long. For example, of acoustic tomography, we're using an acoustic frequency of 40 kilohertz with two coplanar sources in phase for this example. And this is what we have obtained at T0, and after half period, we can see that effectively both speakers were in phase. We have do the same with speakers out of phase, and it works exactly the same way. We also try to use, for example, here 7 coplanar sources in phase and see what happens when we are very close at only 1 millimeter here from.
5 minutes left.
Sorry?
5 minutes left.
5 minutes? Okay, I'm accelerating. I'm almost finished. So we get effectively the 7 sources separated. And if we are at an altitude of 25 millimeters, we can, in fact, validate the Huygens principles in acoustics. We have done also the same thing with acoustic LIDAR. So this time we decided to remove the solid target, and we're just using droplets as a target. For example, here we have some small droplets, and we are emitting a sound wave in direction of the laser beam, which is pointing on the droplets, and see what happens. And we can see, so that's very, very new, so we have not so much results. And we can see that effectively the result obtained with the traditional microphone and the result we obtained with our laser microphone was not so far away. So it's interesting because in this case we have no more solid targets, so it's much easier to use in the real life. But we still need some targets, so it may be dust, it may be droplets, doesn't matter. It may be enough effectively to detect sound waves using this sort of system. So the last unusual application I want to introduce, so I will be in time, fortunately. This is roughness estimation. So here we have some different sandpapers with different roughnesses. And here we can see we have the same roughnesses but different colors. So we glue this on a rotating motor. We translate our laser system. And what we have obtained is some signals like this. In fact, we are not measuring this time the Doppler frequency. We are not anymore measuring the fringes. We are just detecting the shape of the optical power. And by detecting the amplitude of the shape, we are able to find information. Unfortunately, we can see that for the same roughness, if the color of the target is different, the signal, the amplitude of the signal is also different. So we want to, in fact, be insensitive to this color. So here, the signal is a function of here the reflectivity of the target. The signal, the useful signal, because we want to do some profilometry, and some noise due to speckle that may be filtered. We are using a leaf filter, for example, just a multiplicative noise, so it's not so, so disturbing. So the idea was to remove the reflectivity dependence of the signal to get only this information, knowing that we have filtered the speckle noise. So we are using, in fact, two laser heads, two systems, focused at two different distances. And we can see here that at one given focus distance D1 and the other one D2 of both systems, we have the maximum of the amplitude. That's normal. But doing some calculation, I will not enter in detail, we have created a bijective relationship, which is this green line. So that was theory. In practice, we still have this green line between here and here, both optical focus distance of each system. And then it means that we have only one possible solution in this to get information about, in fact, the roughness of a target. So here we use it for example, this kind of target with different shapes, and this is what we have obtained. And here we compare what we have obtained with our system with a confocal microscope. Of course, we are not as accurate as a confocal microscope, but it's much cheaper and it can be embedded, so that's really interesting. A last point, and I will finish with that. In fact, when I show you those fringes, beautiful fringes with sort of like signal and so on, I'm lying somewhere, because in reality, well, we have also high frequency oscillation on every single fringes, and which are removed because they are filtered by the bandwidth of the photodiode and of the electronics. But from, if we're just considering the physics, we should have also here those high frequency oscillation, and in every fringe we prove that we should have also information about the reflectivity of the target and the absolute distance from the laser to the target. I will finish just by a global conclusion. This is not a work I'm doing alone. So about acoustic and velocimetry, Julien Perchou and Adam Gold are working a lot about this. I'm much more specialized in vibrometry with Olivier Bernal. And I'm also working on the project with roughness measurement with Francis Bonny and Bastien Grimaldi. If you have any question, because I fear it was a little bit too long, you can still write me. This is my email. Sorry for being a little bit too long. I finished. Okay. Thanks a lot.
Thank you very much, Thierry, for a very interesting talk. It's very interesting to see what can be done with just a laser diode and the signal it generates. So I think we have no time left for questions. So as you suggested, you can be contacted by email if anyone has an interest. Just again to thank you for your participation and for accepting our invitation. It has been a pleasure to hear you on your research activity now.
Thank you for inviting me, and sorry for the fact that I'm still not speaking Spanish.
Well, I'm not speaking French also already.
Okay.
Thank you very much, and let's